All right. So still some topics are pending in our discussion of the cardiac system, especially cardiac control and the concept of the ECG, the electrocardiogram. However, before we foray into this area, we'll have to start the second module of this course, which is the spark of life. And see how electricity is related to the human body. And it's really important to understand how electrical signals propagate in the human body. They are a very crucial aspect of our existence. They control how we move, how we respond to certain stimuli. And when you involve electrical propagation in muscle fibers, they also control how the heart pumps. The body, if you look at the human body, it has a certain resistance. Whether it's an insulator or a conductor, this has to be answered. Why do we get an ECG signal? Why do we have an EEG signal? Why do we have an electromyograph, a signal from the muscles, and so on? So we'll have to discuss the interrelationship between electricity and the human body. There's another aspect which is important, is biomagnetism. Whether magnetic fields are important when we are discussing the human body. But magnetic effects are generally orders of magnitude weaker than electrical effects. So while some organisms may have profound, conspicuous magnetic effects, the magnetic effects in the human body, they are much smaller than their electrical counterparts. So we'll not be discussing about biomagnetism at all, even though when you go to a hospital, and God forbid you are in some sort of a situation in which you would like to have an MRI taken. The MRI is magnetic resonance imaging, and this is based upon the intrinsic magnetism of the human tissue. All right, and we have an expert on MRI sitting right with us today, Dr. Hassan. Anyway, so we'd like to talk about electricity and the human body. But since this is a 100-level course, and some of you might have not taken a course on electricity and magnetism, I would just like to give a quick recap of the basic concepts of electricity. And I'm dropping off the magnetism part. And so this, most of it will be a refresher from your FSC or A levels, but still it's worthwhile to do a quick brush up of basic concepts in electricity. Of course, we all know what charge is. Generally represented by the symbol Q. So if I have a charged place at some point in space, it's going to produce a field, an electric field. All right. And this electric field is a vector. So surrounding this charge, there is a medium. This could be vacuum, could be space, could be water, the cerebrospinal fluid, the fluid inside the cell, the fluid outside the cell. So this charge is in some fluid. For example, this could be an ion, a sodium ion, potassium ion, or a chloride ion. So surrounding this charge Q, there has to be a magnetic field, and this magnetic field is computed at some point in space. Let's call that point P. So with respect to this charge, suppose this is a positive charge, there is going to be an electric field at point P. And that field will, of course, depend upon how large this charge is. So I could write, so there's a formula for the electric field from a point charge, and that is given by 1/4 pi epsilon Q over R squared in a particular direction. So suppose this distance of this point in space from the charge itself is R. So this would be the electric field. It depends upon how large the charge is. It's an inverse square law, inversely proportional to the square of the distance from the charge. And of course, it has to be a distance as well, a unit vector that is coming radially outward from the charge. So you just draw a line between the charge and the point of interest and extend it onwards in the same direction. So radially outward pointing field. Likewise, you can find the electric field everywhere. So here the electric field is going to point in this direction. Here it's going to be in this direction. Here it's going to be in this direction. So there is a radial field outside this charge. This quantity here is called the permittivity. All right. So in vacuum, this is generally denoted by epsilon naught. And in different media, for example, in water, if this charge is placed inside water, the permittivity would be the permittivity of vacuum multiplied by some relative permittivity. So for water, epsilon r has a value of about 80. All right. So now this is what we know about electric fields. These are vectorial fields. They are vectors pointing out in space. All right. So now what we could also imagine is the following. Suppose I have two plates, metallic plates, they're conducting, and I put charge on these plates. And I put a positive charge, capital Q, on one of the plates and a corresponding negative charge on the other plate, minus Q. And suppose these plates are very long, very tall. All right, so ideally they go to infinity. Now, does anyone know what this resembles? This is a capacitor. This is like a capacitor here. Okay, so I'm bringing in these concepts because they are all going to apply to the human body in one way or the other. So now inside these plates, there is going to be an electric field. That electric field is going to be pointing from the positive charge to the negative charge. And the field lines are all uniform, which means that if I were to take a point here, P, if I were to take a point here, R, here, S, all of these points will have the same magnetic field, both in direction as well as in magnitude. All of them are pointing from left to right. So if I were to draw a magnetic field at S, this is what the field looks like, a vector. This is what the field looks like at Q. This is what the field looks like at P. At each point, the field is pointing in the same direction and it has the same magnitude. So it's a uniform field. And no field leaks out of the capacitor because the plates are assumed to be very large. If the plates are finite, then this field, of course, is going to fringe out like this. But we ignore these end effects. Now, what would be the electric field in this particular case? There's no single charge, there is a distribution of charges. So there has to be a formula for this electric field as well. All right. So if I were to jump ahead a little bit in terms of your knowledge of electricity, this electric field is going to be proportional to the amount of charge that exists on a plate per unit area. So I take this plate, take a small amount of area of this plate and find out how much charge is on that small area, right? So let's call that surface density of charges sigma. All right. So E is going to be equal to sigma over epsilon. Let's suppose this is vacuum, sigma over epsilon naught in a particular direction. Let's call this the Z direction. So this is a unit vector pointing from the positive to the negative plate. Now here, this formula is quite different from this formula. So one naive approach, if you hadn't studied the electricity, you would break up this charge into small units and find out the field due to one charge and the next charge, but it becomes impractical to do so. So you have to come up with a different formula. And that formula is derived from what is called Gauss's law. So I would not go into this derivation at this point, but you remember that whatever charge distribution you have, say in a capacitor, you should be able to tell what the electric field is. All right. Now, what do you think would be the units of this sigma? Charges per area, coulomb per meter square, for example. All right. Now, how do we know what is the direction of the electric field? How do we determine directions of an electric field? So I could have drawn the electric field in the opposite direction as well. But what determines what my direction is? Right. So if I take a test charge, Q prime, bring it here, and just leave it there, starting off at rest, it's going to accelerate in a certain direction because a force is going to act on this test charge. That force is called the Lorentz force, is given by the test charge multiplied with the electric field. All right. So if I bring in a positive charge and leave it here, a force is going to act on it. And this force is going to accelerate the positive charge from the positive side to the negative side. So the direction of acceleration or the force tells what is the direction of the electric field. All right. So now this brings me to the concept of potential energy and potentials. In electrophysiology, we talk about membrane potentials and activation potentials, resting potentials. So it's useful to understand what is the meaning of a potential. Any questions up to this point? All clear? All right. So let me redraw this capacitor here. Large metallic plates. And this is the direction of the electric field. And I bring in a positive test charge. Sorry. I bring in a positive test charge. I place it near the negative side, Q prime. Okay. Now, suppose I draw an axis. This is my x axis. This is 0. And this point is x equals d, the distance between these plates. All right. Now I take a tweezer and put that positive test charge here on the negative plate. Now what's going to happen is if I leave that charge right here, it's going to annihilate in this negative plate, but I don't let it do so. I do some work. I bring in some energy from my muscles, hold this charge with the tweezers and move it from x equals 0 to x equals d. I'm going against the electric field. So I have to do some work here. I have to bring in some energy. I have to use some energy from elsewhere, say the chemical energy stored in my muscles, so that I can move the tweezer and bring it from the negatively charged plate and move it uphill in the electrical landscape. Move it uphill and move it towards the positive plate. So what I'm doing is, if I were to plot the energy of this test charge as I move it against the potential, against the electric field, I'm going up in energy. So I start off from 0 and I go up in energy in a straight line. And how do I know it's a straight line? I use the work energy principle, which you've learned from basic mechanics. I know that if I have a small amount of a force that is acting through a distance dx, it requires a certain energy to do so. All right, we've already seen this formula in one of our previous lectures. Now here the force is going to be QE, Q prime E. So if I move this charge in such a way that at each point, I'm moving this charge with a steady velocity, which means at each point, I apply an external force which is equal to Q prime E. Then I'm able to move this charge uphill in energy. And this would require a certain amount of work in each step, which is dW. Okay, so I'm quasi-statically moving this charge slowly, slowly, slowly. At the end, when I reach this point D, I would have done some work. And if I were to calculate the total amount of work that I've done, Q prime E, now E does not depend upon X because it's uniform throughout. I would need to integrate this expression. Okay, and my limits of integral will be X is going from 0 to small d. So this work will be Q prime E d. So when I reach at this end, the energy has gone up to Q prime ED. Now this is the energy stored inside this charge. All right. It has gained potential energy. And we say that the charge has gained some potential energy. All right. So this work done on the charge increases its potential energy. All right. So this is the potential energy of the charge at a distance d. The potential energy at a distance x would be Q prime E x. This is just like having a chair here. So this is my chair. If I step on the chair, I'm going against the gravitational force, but I have to apply a certain amount of energy to do so. And that energy will be mgh. All right, so exactly an analogous situation over here. Now this is the potential energy of this charge. Now if I were to divide this potential energy by the amount of charge, I would get Ex. And this is what is called the potential at this point. So if I were to take a point X, the potential energy is Ux, and I divide it by this test charge, because the test charge is arbitrary. It's just put in as a fictional element. It's just put into the story. It's a test charge. So I need some strength of the electric field here, which is independent of the test charge. So I divide it by the test charge. So I make this value is called the potential at this point. The potential is like a field. It's the potential at this point. All right. So whenever you have a distribution of charges, there's an electric field. Test charges will have certain potential energies, also called electrostatic or electric potential energies. And inside space, there is going to be a potential. And potentials are measured in volts. And remember, we took this x equals 0 to be the datum point, the reference point. All potential energies and energies are measured with respect to this point. So the potential is with respect to something. Okay. So I could say that the change in potential is going to be E, the change in distance. All right. So if I look at this expression here, from the potential, I can also derive what the electric field is going to be. And this is written as delta V over delta X. And if I take the limit that this delta X is really small, this becomes an expression of this kind, dV over dx. And generally, I put a minus sign here as well. And the reason for this is the electric field here is pointing from left to right. But as I'm going from right to left, the potential is going up. That's why in order to make everything notationally consistent, I put this minus sign over here. So whenever I have a potential, I can differentiate this with respect to, say, space and get an electric field or a force. Multiply this electric field with charge, I get a force. All right. The corresponding equation for forces is minus d u over dx. Okay. The rate of change of potential energy is a force. The rate of change of potential is a field. All right. So is this all making sense up to this point? All right. Now I would like to inch closer and closer towards electrical conduction. How does conduction take place in the human body? Okay. Yes, please. Potential difference between? That's what we are getting to. Right. So we need to understand. So there is a potential difference between the two sides of the membrane and in a neuron or a muscle cell. But you want to do some quantitative measurements of how much that potential is going to be. That's why I'm bringing in this background. Okay. Now the next question is about conduction. Electrical conduction precisely. How does electricity flow? And what is the meaning of flowing electricity? Now, electricity charges can flow whenever there is some potential difference, right? So if I take a piece of metal, we're familiar with flows in metals, right? That's what you do on a daily basis. You see electricity in your wires. So this is a piece of metal, copper. Now, if charges are flowing, so I assume that my charges are positively charged, just out of conventions, my charges are flowing with some velocity, the drift velocity, there has to be some driver to this flow, because this object, of course, has a resistance. Like the pressure equations that we saw, the pressure gradient causes flow of fluid. Here, a potential difference between these points, some potential difference between these points is going to cause the flow of charge. Now, when there's a potential difference from here to here, charges would also like to go downhill. So if I were to plot the potential energy of charges from point A to point B, and I plot the potential of this positively charged from A to B, the potential energy must go down. All right. Because if this were a superconductor, for example, it had no resistance, there would be no requirement of potential difference. But here you need to have a potential difference, which means you also need to have an electric field, because a potential change is associated with an electric field, as we've seen. So what would be the direction of this electric field for charges to flow from A to B in a metal? From A to B. So there has to be an electric field here, A to B. Now, where is that electric field coming from? First of all, remember, if you do not have any moving charges and you take a metal and put charge on it, in equilibrium, there can be no electric field inside the metal, right? So if I were to take a sphere or some metallic object, put it on on an insulating stand and drop charge on it somehow by touching it with a charged subject or bringing another charged object close by and grounding it. So somehow I distribute charge on it. All of that charge is going to live on the outer periphery of this surface. It's not going to go inside. inside the electric field is always going to be zero. But this is true only for the static case in which charges are not flowing. But whenever you have a current I, charges are flowing, there has to be a change in the potential energy, which means there has to be an electric field. Now, where is that electric field coming from? From the battery. Okay, so this is a nice answer. So if I have a battery, let me draw a battery. So this is the positive terminal of the battery. This is the negative terminal of the battery. Now I connect the positive and the negative terminal of the battery by a wire. Connecting wire, metallic wire, copper wire. So I connect the two terminals by a wire. Okay, let me just interrupt the wire. So I leave a gap here. So I don't close the circuit, I just leave a gap. Now, this rod, positive rod, will still have an electric field, wouldn't it? This negatively charged conductor will still have an electric field. So electric field exists in this case as well, but why doesn't the current flow? So it's not just connecting to the battery, in fact, there's more to it. So what's going to happen in this scenario is that this is a conductor, this is a conducting rod of charge. This charge is going to be distributed on the surface of this conductor instantaneously, almost instantaneously, right? And this negative charge is going to be distributed on the surface almost instantaneously. All of this wire will be at the same potential as this conducting piece. All of this wire will be at the same potential as this negatively charged rod. Everything is at an isopotential state, same potential everywhere here and same potential everywhere here. Now, when there's no potential gradient, no potential difference, there can be no electric field, and therefore there's no flow of charge. All right. So it's not just the electric field due to the battery. Now, if I zoom in my attention onto this region here, so let's call this point A, let's call this point B. Now, this is instructive because it's going to help us understand how nerve conduction takes place. So this is my section A, this is my section B. Now, all of this positive charge on the surface, there has to be positive charge on the ends as well, sorry, and negative charge here. All right. Now, there has to be an electric field here, right? So this gap acts like a tiny capacitor, an electric field here. All right. So capacitor is formed here. Now, if you look inside the metal, let's take a point P. If you look here, there can be no electric field inside the metal. And the reason is that if there were electric field, charges would flow, but there are no charges flowing here. So inside this wire, there has to be zero electric field. But the point is that these positive charges do produce an electric field inside as well, don't they? Suppose this electric field is represented by this vector. This is the electric field due to the end charges. All right. But the electric field here must be zero. So there has to be opposing electric fields inside the piece of wire. So here, if I look at this point, these end charges are going to produce an electric field in this direction. At this point, these electric fields are going to produce an electric field in this direction. All right. But these electric fields produced by the ends, they must have to be counterbalanced somehow so that the electric field inside remains zero. Now, these are counterbalanced by the distribution of charges that exist on the lateral walls of this conductor. All right. So this lateral side will produce an electric field that is, say, pointing here. This will produce an electric field that is pointing here. And the entire distribution of charges must produce an electric field that is counteracting or counterbalancing this electric field. So at this particular point, at each point, the delicate balance of charges throughout this conducting regime, they produce zero electric field. All right. Now, why is this important? So this is like feedback control. There's a distribution of charges. Those distribution of charges produces electric fields in such a manner that inside the wire, the fields are totally cancelled out. Now, somehow, if you stitch these two pieces of wire together, a closed circuit is made. So now what I'm going to do, I'm going to plug this gap. Nothing happens to the lateral charges at that particular instant in time. So suppose I plug this gap at time t equals 0. Now I'm drawing the charge distribution a slight infinitesimal time later, right after the gap has been stitched. What's going to happen is that the end charges, they are going to annihilate one another, right? Positive and negative charges, they are going to merge and they're just going to go away. But these lateral charges remain. So now at this point, what has really happened is that these red electric fields, due to the gap, they have just diminished. So this information travels at the speed of light from the gap to these points, and these red vectors just dissipate, they just go away. But the lateral charges remain, so these electric fields remain intact for an instant after the gap has been plugged. Now, if I were to draw these electric fields here, what would this mean? This means that there's a sea of electrons inside this conductor, and it tries to move the charges away from the lateral sides, right? Charges are moved away from the lateral side. On the in this side, the charges are moved towards the lateral walls. So the red electric fields, due to the gap, due to the capacitor, they just disappear. And these residual electric fields, due to the surfaces, the lateral surfaces of the conductor, they remain intact. And they cause a sudden redistribution of charge. So there is charge inside this conductor available because there are free electrons that are available. So if you look at the direction of this electric field, this is going to move the positive charges away from the surface. Away from the surface. On this side, the positive charges will be deposited on the surface. So here the positive charges are diluting. Here the negative charges are diluting. And this information then travels at the speed of light throughout this wire. Local electric fields are set up. Those local electric fields produce redistribution of charge on this conducting surface. And when equilibrium has been regained, let me show you what the charge distribution is going to look like. Battery, positive terminal, negative terminal, inside an electrochemical bath, ions everywhere. Here is my wire, which is now made into a closed circuit. Now I'm going to draw the charges. Positive charges here and a very high concentration of them. Positive charges here, high concentration. But as you approach this point in the exact middle, the charge distribution dilutes out. So concentrated this surface charge density here, and it just dilutes outwards in the exact middle, at the middle length of this wire. There is hardly any charge left here. And here you have a very dense distribution of negative charges. But then gradually they spread out, they dilute. So this is the surface charge distribution. Whenever you have current flowing through a wire, there has to be a surface charge distribution. The surface density of charges on the surface, they are not uniform. So if I look at a certain section of this wire, if I take a certain section of this wire and plot it here, and I take two ends, let's call this end C, let's call this end D. So here I have C, here I have D. I take a band here. So this band will have some distribution of charge. At the neighboring band, in the proximal end, distal end, there is some distribution of charge, but this distribution is weaker, diluter than this distribution. So there is a charge gradient. And when there's a charge gradient, this acts like a capacitor. A differentiation of high potential energy area from low potential energy area. And this produces an electric field inside the conductor in this direction. This electric field causes a current to flow, right? So a current is going to flow I, which could be number of charges per unit volume, the cross-sectional area, the velocity, and so on. Or a current density. Generally, you talk in terms of current densities. Ampere per meter square is proportional to the electric field. And there's some constant of proportionality that is called the mobility of charges. All right. So in order for current to flow, there has to be a gradient of potential energy, a gradient of potential. Gradient of potential, potential difference and current, ये लाजिमो मलजूम है, एक दूसरे के साथ साथ चलते हैं. There has to be a potential difference for current to flow. Of course, if you have a finite resistance or a finite conductivity. Exactly the same concepts apply to conduction in the nerves or in the muscle fibers. The mechanism is different, but an electric field is set up, a potential gradient is set up by some mechanism. Here, the potential gradient is set up by local electric fields and by a feedback mechanism. Right? So when we plugged this gap over here, so there were electric fields inside, but they all counterbalanced in a delicate balance so that the field inside was zero. Now you plug this gap. These electric fields disappear. The fields due to the gap charges disappear, but the fields due to the surface charges remain intact for an infinitesimal period of time. Those electric fields cause redistribution of the charge momentarily in this local region, right? And they try to dilute these charges. And this wave of dilution spreads out from here all the way to the battery. Eventually, a state of equilibrium is restored in which a gradient of charge distribution is achieved. And if you were to move, if I were to draw, so if this is my x, this is my potential x, and my x variable starts from here, right? So as I move here, my x is going up. Here it's half of the length going up here and then to the other side, and then I have to come back here. So if I were to make a graph of this potential is going up in a uniform fashion. This is my, let's call this terminal B, terminal A. So this is my terminal B. Here I have my terminal A. Now I have to go back from A to B. So I get a sudden drop in the potential energy. This is, say, Z, where Z is this, the distance between these two electrodes in the battery. Okay, so this is my potential gradient along this circuit. As I circumambulate this circuit, this is what the potential profile looks like. I start from B, low potential, go up to A, the highest potential, which is the positive side of the battery. Then it suddenly drops from A to B. Okay. All right. And in terms of battery, if you look at the battery, the electric field inside the battery is much larger than the electric field in here, because the slope here is much larger. Right? This point, this difference is also called the EMF of the battery, electromotive force. Now, this is what I wanted to discuss about non-biological systems. First of all, there's a charge. Charge produces an electric field. The electric field imposes a force on any test charge. That force causes the energy of the test charge to change. That energy is called the potential energy. There's a landscape of potential energy. You move from one end to other. The potential energy can go up or down. If I remove my attention from how much my test charge is, I can define a potential of the field. That potential is V. The potential is high or low. Going from low to high potential means the potential energy of a positive charge is going up. Current flows because of a potential gradient. In normal conductors, in normal life, that potential gradient is brought out by surface charges. Then you can do experiments, and we do such an experiment in a classroom demonstration, electromagnetism, in which you can measure these feeble charges on the surface. So this surface of a conducting conduit is charged, even though the charges are really small. And this redistribution of charge takes place because of a control mechanism, feedback mechanism. The charges themselves are moving really slowly in this local region, but the information of charge distribution is traveling at the speed of light. So even though the drift velocity of charges locally can be very small, few millimeters a second, but you turn on the switch 1 kilometers away, a light bulb will immediately light up. All right, so flow of charge requires a potential gradient. And of course, you need to know what the resistance is. So we know the Ohm's law. The Ohm's law, I, is the potential gradient divided by the resistance. And the resistance generally depends upon what material the conductor is made of, how long it is, and how broad it is, how wide it is. So the resistance is generally given by, for a nice cylindrical conductor, rho L over A, where L is this length here. All right, and A is the cross-sectional area. And rho depends upon the material. Sometimes this Ohm's law is also written as I equals GV, where G is the reciprocal of the resistance, generally called the conductance. And this is the kind of form that is used when we discuss action potentials. So any questions about these basics? Yes. The charge distribution is also varying linearly. So I can't draw it at the flick of the time. I can't draw a linear charge distribution, but it's also varying linearly. So the datum, you can fix the datum anywhere. You can bring this graph down so that there's a sign change in the middle. So the datum is what is your reference. So I can bring this potential graph up and down as per my will. So now in the middle of the conductor, my potential is 0. That's how I define it. Now the next question, we're going to start off the next lecture by talking about the neuron. How does conduction take place in a neuron? It's a totally different mechanism, but a really interesting mechanism. There are ions at play here. Right now, we have no mention of ions whatsoever. We have free electrons inside the conductor, electrons that are free to move. There is no matter transport, right? In this system, there is no matter transport. But in a membrane, in a cell membrane or a neuron, there is active and passive transport of ions due to concentration gradients and due to extra pumps which move ions in and out of the membrane, and that helps in conduction. So we're going to look at this process in more detail in the next lecture. Today I'm going to upload a homework that will be due next in the next class. So please bring in your homeworks for the next class. And you can work in groups of 4 people, up to 4 people. Thank you very much.